For part 4, we're graphing equations, and we're starting off with a polynomial function. And the first thing I'm going to do is I'm going to graph it in the standard viewing window and see what it looks like. Here's what the graph looks like in the standard viewing window, and because it's a third degree polynomial, so the degree is 3, and it's odd, because 3 is an odd number, and the lead coefficient is also 3, but that 3 is a positive number, I know that odd positive equations go down to the left and go up to the right. So I definitely have that left and right hand behavior going on. But I'm missing, it looks like, a maximum point, and it looks like I'm missing a minimum point by using the standard view. So what I'll do is I will adjust my values based on the table. When you look at the table of values, it looks like this graph goes up until about 50 and down to about -40. So maybe what I'll do to give myself some space, I'll graph from -10 to +10 for my x's because my left and right hand behavior was correct. But what I'll do is I'll graph from -100 to +100 for the y's to make sure that I have these high and low points on my graph. So when you change your viewing window to match that, this is what it should look like. And the question said we needed to make sure that we saw the intercepts. This one has 3 x-intercepts, the y-intercept, the maximum and minimum point. So all of those appear on this viewing window. To find the y-intercept, we're going to go back to the table and get the value when x was equal to 0. So in this case, when x is 0, y is 24, so the y-intercept is the point 0, 24, and that's that blue point that we see there. The zeros are the x-intercepts. And what we're going to have to do to find those x-intercepts is go to the Calculate menu that's above Trace on your calculator. So we're going to go second, Trace. To get to the Calculate menu, we're going to choose option 2, and then what you're going to have to do is you're going to have to move the cursor to where the x-intercept is, go a little bit to the left along the graph and a little bit to the right along the graph, and come up with a range in which your calculator can find each of these zeros. So for each of the zeros, you have to go to option 2 for the Calculate menu, move the cursor close to where it crosses the x-axis. Then for left bound, keep pressing to the left. For right bound, go past the 0, go to the right. And then for guess, just simply press enter. So this polynomial crosses the x-axis 3 times. That's not surprising because it's an x to the third. It's a third degree equation, so there's at most 3 zeros. And here are the 3 zeros. We have -3, 0. Here we're going to write this as a fraction. 0.666 is 2/3, 0, and I'll show you why we're writing it as a fraction in a few minutes. And then the last 0 is 4, 0. So to find each of these zeros, you have to do this 3 times. Go to second and trace and option 2 for 0, and give the calculator a left bound and a right bound for each of those values. Now to find the relative extrema, the maximum and minimum points along the graph. Here we have a maximum and 1 minimum. We're going to go back to the second trace Calculate menu, and to find the maximum, we're going to go to option 4. To find the minimum, we're going to go to option 3. And just like you did for the zeros, you have to move your cursor, let's say, to the maximum, and then go a little bit to the left, press enter. A little bit then past the maximum to the right, press enter. You basically have to give your calculator a range in which to look to find these relative extrema. So the relative extrema are the maximum and minimum points along the graph. So here the maximum to the nearest tenth turns out to be -1.5, 53.6. That's the maximum. And the minimum turns out to be 2.6, comma, negative 45.5. So those are your extrema values, your high and low points for this polynomial function. Lastly, what we need to do is we need to use synthetic division to verify the zeros. What we're going to do is we're going to take our equation. Remember, the equation that we're trying to graph is 3x to the third minus 5x squared minus 34x plus 24. We're going to take all three of the zeros and we're going to do synthetic division. So let me start off with first negative 3, the x value for the 0. When you divide a 0 into its function, the rule that we had said that there should be no remainder. So here, when we do synthetic division, we should be left with the 0 at the end of the process. Remember, synthetic division, you add down and then you multiply across. So here we're going to add down this 3, multiply across. 3 times negative 3 is negative 9. Add down negative 5 plus negative 9 is negative 14. Multiply across, negative 14 times negative 3 is positive 42. Add down, negative 34 plus 42 is 8. Multiply across, 8 times negative 3 is negative 24. And here when we add down, we get a 0. So this is how you verify your zeros. You divide each of them into the equation. Here I'll take the second 0, which I made into a fraction, and I did that because it's going to make the synthetic division easier. I'm going to take the original equation, I'm going to add down and multiply across, and I know if I do this correctly, if 2/3 is a 0, I should be left with a 0 at the end of this process. So I'm going to add down the 3. 3 times 2/3, that gives you 2. When you add down, negative 5 plus 2 is negative 3. Multiply across, negative 3 times 2/3 is negative 2. Add down, negative 34 plus negative 2 is negative 36. Multiply across, negative 36 times positive 2/3 is a negative 24. So here when I add down, 24 minus 24 is 0. Now we'll take the last 0, which we said was 4, and also divide that into the equation. So this is how you verify zeros using synthetic division. And I did that division for you, so that way you can check your work. So that is how we graphed polynomial functions in our course. This next question has us graphing a rational function. And rational functions are basically equations or functions that are in the form of a fraction. So here's the rational function that we have to graph. And again, just like I did before, I'm going to graph this like I did with the polynomial in the standard view, see what I have, and try to work around that diagram. So here's what the graph looks like in the standard view. And the first step I have to do here is to find the vertical asymptotes, the vertical problem areas of this particular function. And the way you find vertical asymptotes is you set your denominator equal to 0 and you solve. So here you're going to have x squared minus x minus 6 equal to 0. And we're going to solve by factoring. Here it factors into x minus 3 times x plus 2. And when I set each of those factors equal to 0 and I solve, here it looks like being the key, the two vertical asymptotes are x is equal to 3 and x is equal to negative 2. And vertical asymptotes are areas that your graph avoids. So for example, if I look at my graph and I go to x is equal to 3, here is 3 on the x-axis. It definitely seems like this graph has an issue with x is equal to 3. However, it doesn't look like that at x is equal to negative 2, the graph has a vertical asymptote. What you might want to do for these questions is first try to identify if there are any holes in the graph. The holes in the graph are known as points of discontinuity. And a rational function has a hole if there is a common factor of the numerator and the denominator. So we factored our denominator to find the vertical asymptotes. We factored it into x minus 3 times x plus 2. If I factor the numerator, is there a common factor? Well, x squared plus 4x plus 4 factors into x plus 2 times x minus times x plus 2, or x plus 2 squared. You see how there's a common factor of x plus 2? So since there's a common factor, there is going to be a hole. There is going to be a point of discontinuity. The way you find the equation of the hole, because the hole is going to be a point in which the function is undefined. The way you find the point of discontinuity is you set that common factor equal to 0. I'm going to go x plus 2 equals 0, and I'm going to solve. And here I'm going to get x is equal to negative 2. So this graph is going to have a hole at x is equal to negative 2. These holes, these points of discontinuity, take precedence over vertical asymptotes. So that's why you might want to go about finding the holes first when you go about graphing a rational function. Here, this graph is only going to have one vertical asymptote at x is equal to 3. But x is equal to negative 2 is not going to be a vertical asymptote. Instead, it's going to be a hole. So here I have a hole at the point negative 2 comma something. And the way you get the y value of that hole is you take what's left over in the equation after you canceled out the common factor. See what was left over right here? Here I'm going to have x plus 2 over x minus 3. If I now plug in this x is equal to negative 2 into what's left over, here I got negative 2 plus 2 over negative 2 minus 3. I took out the x's. I put in negative 2 because that was the x value of the hole. Here I have negative 2 plus 2, which is 0. Negative 2 minus 3 is negative 5. And 0 over negative 5 is just 0. So that means this particular graph doesn't have a vertical asymptote at x is equal to negative 2. It has a hole at the point negative 2 comma 0. And one of the things that you can do to verify your work is you can go to your table and look for errors. The problem is you're going to have to be able to interpret what these errors are saying. For example, here, the error at negative 2 is telling you that there's a hole at the point negative 2 comma 0. Here, the error at 3 is telling you that there's a vertical asymptote at x is equal to 3. So if you see an error message in your table when you're graphing a rational function, you know that there's an issue going on. You just have to be able to interpret what that issue even is. Next up, what we're going to do is we're going to find the horizontal or slant asymptote of your function. And we're going to start off with the horizontal asymptote. What you're going to do for horizontal asymptotes is you're going to compare the degree of the numerator to the degree of the denominator. You're going to look for the highest power of the numerator and the highest power of the denominator. In this case, the numerator's degree, the highest power of x, is 2, because it's x squared. Here, your denominator's degree, the highest power of x, is also 2. And what's going to happen is n could either be less than d, n could be equal to d, or n could be greater than d. Here, since n and d are both 2, we're going to look at when n is equal to d. What we're going to do is we're going to set up the line y equals the lead coefficient of the numerator divided by the lead coefficient of the denominator. This is what you do when n and d are the same value. So here the lead coefficient is going to be 1 because we have 1x squared for our numerator. Here it's going to be 1 because it's 1x squared for our denominator. So here the lead coefficient of the numerator was 1. Lead coefficient of the denominator is 1. So that means the line y equals 1. That's the horizontal asymptote. If n would have been less than d, remember it wasn't. N and d were both 2 because those were the highest powers of x. But if n would have been less than d, then the x-axis would have been the horizontal asymptote. If n was greater than d, there'd be no horizontal asymptote, but if n was 1 more than d, then what you would do is you would have a slant asymptote. In order to find a slant asymptote, you would use synthetic division. So this particular problem, we saw that n was equal to d, so the horizontal asymptote is the line y is equal to 1. Next up, we want to find the x-intercept, or the zero of the function. And we're going to be using the same technique that we used to find the zeros of a polynomial. We're going to go to our Calculate menu, second, and then Trace, and choose option 2 for zeros. And it looks like here, based on the calculator, it tells you that there's a 0 at the point -2, 0. However, we learned from before that -2, 0, there's a hole in the graph. So actually, we're going to write down that there are no x-intercepts. There's no zeros. Again, that's what makes graphing a rational function a little challenging, in that you might go about using your calculator to find certain values, but for rational functions, the values that it gives that the calculator might give you might be incorrect. So that's why here, remember, the holes take precedence over any asymptotes or zeros. So in this case here, even though it looks like, according to our calculator, there's a 0 at -2, 0, there actually isn't. So even though our calculator says there's a 0 at -2, 0, we know that's simply not the case. And now finally, to find the y-intercept, we're just going to go to our table and look when x is equal to 0. So here, when x is equal to 0, our y-intercept turns out to be -2/3. So the point 0, -2/3 is our y-intercept. Now finally, what we're going to do is we're going to sketch the graph in a window that displays the asymptotes, the holes, and the intercepts. And the good thing about these rational functions is that most of the time, the standard viewing window is sufficient for seeing all of those items. Here we saw that there was a vertical asymptote at x is equal to 3, so I'll go to about 3 on the x-axis and draw the vertical asymptote. Here we saw that the line y is equal to 1. If you go to your graph and you go along the y-axis to 1 and kind of extend it, you see that each of these branches definitely does avoid that line y is equal to 1. So what I'll do is I'll go to my graph and I'll go to 1 on the y-axis and draw a dotted horizontal asymptote. Here we saw that there was a hole in the graph at -2, 0, so I'll denote that by drawing an open circle at the x-axis at -2. We say there were no x-intercepts, but there was a y-intercept. There was a point at 0, -2/3. So here's what my graph looks like. It kind of goes underneath the asymptote. It has a hole in the graph at -2, 0, and then there's another branch up in the right-hand corner for that function. So that's how we're going to go about graphing rational functions.